We're doing control systems, and we already talked about the transfer function. You're not always handed a transfer function for the system you're interested in. Sometimes a bigger system is represented by a block diagram that's composed of smaller systems. So each little system has its own transfer function. So let's talk about block diagrams a little. You've probably seen functional block diagrams, I don't know, to show workflow or some business thing or something like that. For us, when we work in the Laplace domain, it's actual arithmetic. It's not just sort of a notional functional relationship. It's actual arithmetic. Take this. We have an input U and an output Y, and something happens between them. So that's a little transfer function. The blocks in a block diagram or processes are their own little transfer functions. What are on the lines in a block diagram, and they have arrows, are signals. So this is an input signal, this is an output signal, and this process converts the input to an output. That's what signals and systems is all about. Signals being sequences of numbers are functions, function of time. Anyway, let's look at, say, you have two processes in series. The way to go about a lot of this, at least to begin with, is the algebra of it. Let's label every signal here. We'll call this in-between signal A. So this signal A is this process times U, G1U. You just multiply. See, that's the beauty of Laplace transforms. And then this signal is G2 times A, but A was G1 times U, do the algebra, and what you find out is when you have processes in series like this, you just multiply the two transfer functions. Sometimes we call these guys gains. Sometimes they're called filters, sometimes they're called systems, sometimes they're called transfer functions. What about two in parallel? Well, first off, when you see a signal split like this, it means it's the same signal on all these lines. Arrows have meaning. And here's a new piece of symbolism. It's a comparator or adder or summer. It adds signals. And these little signs, plus or minus, tell you whether they add or subtract. So let's do the same kind of thing. This A2 is G1 times A1. And A1 is just U. This A3 is G2 times also. This guy is the sum of A2 and A3. Put all that together, you got a little bit of algebra. And this output, or what happens when you put two processes in parallel and add them, you just add the two processes. That's how parallel transfer functions add. Now here is a loop that's going to be very important. This is your basic feedback loop. And technically it's a negative feedback loop because of this sign here. I like to think of this mentally as think of cruise control. This is the speed you want your car to go at. The output is the speed it's actually going at. That speed gets sensed somehow. You compare that sensed speed to what you want it to be. And depending on how much difference there is, you would add throttle or take the throttle off. That goes into how the car works. So the feedback loop, you'll ultimately get sort of the output speed will tend to be your desired speed. Have this done right. But let's do that algebra. This signal here, right after this comparator, is R minus B. And B is H times Y. So what is Y? Y is G times U. Add what U was, that little bit of algebra. Complete the algebra. I won't go through all that here. You end up with the total output over the input transfer function is this thing. It's the forward path gain or forward path transfer function divided by 1 plus that forward path transfer function times the feedback path gain or transfer function. G over 1 plus GH. And I say just memorize this. This is a very key block diagram. You'll see it over and over again. Forward path gain, feedback path gain, and the overall transfer function. Here's these relationships. Let's see how this works. Here's a block diagram configuration in the way we just saw it. Assume this is a minus. Plus here, minus there. Well, this is that basic feedback path. This is the G, our forward path. This is H, our feedback path. Here's the formula for the overall output over input. Here's the G. Down here in the denominator. And here's the H that goes in the denominator. And after this, you just algebraically simplifying. You get this. Here's your overall transfer function. Output over input. And what's the characteristic equation? This denominator set to 0. Roots of this equation are the poles of the system. Here there is a 0 at minus 1. About this guy? Well, you can kind of see it's also in that basic feedback configuration. In this case, that feedback gain, there's no block there, so the feedback gain is effectively 1. Here you have a little loop, a little inner loop that is also in the configuration of that basic feedback gain. So just for this little inner loop, the G is 1 over S, H is this 2 zeta omega n. So here is the G over 1 plus GH, simplify it to this. And then this little transfer function can replace this whole inner loop. Then I have 3 processes in parallel. So the overall transfer function of this whole forward path will be omega n squared times this guy's transfer function, which we just said was that, times this thing, 1 over S. That's what that is. And now this thing becomes the new G of the whole thing. H is 1. So G, this G, there's a G in the numerator, over 1 plus GH. It's the same G. H is 1. Simplify it to that. And lo and behold, coincidentally or not, this is the transfer function of the prototype of second order system. So this little block diagram is one way to represent a prototype second order system. I got time for about one. Sometimes the block diagrams are nothing but integrators. And I've seen block diagrams where these integrators, sometimes they use a triangle instead of a rectangle to represent them. Well, let's say we were given this top block diagram and we need the overall end-to-end transfer function. Well, each integration time domain is a 1 over s in the Laplace domain. Okay? Taking a derivative is multiplying by s, taking integral is dividing by s. Each of these integrators is 1 over s in the Laplace domain. And I'll label the signals at here, here, and here as A, B, and C. Then we'll just do the algebra. Here's where we're left off. A is U plus C. B is A over S plus Y. And we had what A is, so it becomes this. And then C is just B over S. We have what B is. So now we have C in terms of C. So algebraically solve for C. And I won't go through this, but you end up with C is this. Where now it's only in terms of U and Y, which is what we want to get it down to. And what is Y? It's C over S. And Y equals C over S. We had what C was. And now we have Y in terms of itself, solve for Y. We'll go to that algebra. Here is the overall transfer function, output over input. Just by labeling the signals and doing the algebra. More for next